We're going to look at the power rule for differentiation and finding the derivatives of exponential functions in this lesson. If you want to print the sheet that I'm going to use for these notes, you can go to this bit.ly link and print that and make it easier for you to follow along. So a few quick notes in case your teacher or hasn't told you, or if you forgot what differentiate means. It is simply a verb meaning to find the derivative. And a function is said to be differentiable. If differentiate is synonymous with a derivative, then differentiable at a point means the derivative does indeed exist. A function that is differentiable will also be continuous, and there are some characteristics where the derivative will fail to exist. I'm not going to talk about that in this video. I just wanted to talk about the word differentiable for a hot second. So let's talk about the power rule. So this is a rule for finding derivatives quickly, meaning we're not using limits. And the power rule can be used for any function that resembles or can be changed to resemble a polynomial. So just to remind you what a polynomial is in its strictest definition, it is a function that is written in that could be the sum of terms in the form of a times x to the n. A is any real number. It could be a fraction. It could be irrational. It could be rational. Any real number. N is a positive integer, also known as a whole number. So that is strictly what a polynomial is. N must be a positive integer. However, the power rule can be applied to things that resemble polynomials, and the change is that n could be any number. So you can use the power rule anytime you can write your function in the form of a times x to any number power. It could be a fraction, it could be a negative number, it could be an irrational number. As long as it's a times x to a number power, then you may use the power rule. So let's talk about what the power rule is. And the rule itself is this: if you have a function in the form a times x to the n power, then the derivative of that function, and I prefer Leibniz notation, dy dx, would be a, and the trick is you bring the exponent down and multiply it by the a, so a times n to the times x, a times n times x to the n minus 1. And you may have noticed a little watermark showed up in the bottom corner there. I'm having some issues with my software with this thing that I use to write, and it's been irritating me all day. Hopefully it doesn't completely poop out on me. So there is your rule for the power rule, your formula for the power rule. Let's do a few examples of that. Starting with number 1, if y is equal to this 9x squared 4x squared plus 9x cubed, there it goes again, then the derivative would be what? And so let's see what that derivative would be. Well, the rule says you multiply the exponent by the coefficient. And so 4x squared, the 2 times 4 is 8. And then you subtract 1 from the previous exponent. So 2 minus 1 is 1. Repeat the process for the 9x cubed. 3 times 9 is 27. X, 3 minus 1 is 2. And there is your derivative. Now, it looks really silly with 8x to the first. So you definitely can leave that as just 8x and not actually write the exponent of 1. I just wanted to write it to be painfully clear that I did indeed subtract 1 from that previous exponent of 2. That watermark is driving me crazy. Hopefully I don't cuss any during this video. All right, so let's move on to this one, y equals 5x. If you really want to follow this rule to completion, you can think of that as 5x to the first, and then the derivative, and I'm going to get lazy. I'm going to go down to Lagrange's notation, the y prime. And if you bring the 1 down, 1 times 5 is 5. And it would be x to the 0 power, but x to the 0 power is just 1. So it'll be 5. So 1 minus 1 is 0. And so the derivative of 5x is just 5. And for 3, y equals 7, there is no variable. So again, if you really want to be thorough with the use of the power rule, you can think of that as 7 times x to the 0 power, and the derivative. Bring down the 0 times 7 is 0. And I guess technically it would be x to the negative 1, but 0 times anything is 0. And so it turns out the derivative of 7 is just 0. Now for these last two, numbers 2 and 3, you can make a lot of sense of those if you think graphically. And boy, I love to think graphically. My students get kind of irritated at how much I talk about loving to graph. But let's think about the graph of y equals 5x. That is a line with a pretty steep slope that goes through the origin. And one thing to remember about derivatives is their primary purpose is to tell you the rate of change of a function, and rate of change is translated to slope. So the purpose of a derivative is to find the slope of a function. Well, if your function is a line, then any point on that line always has the same slope. Anywhere I look on this line, it will have a slope of 5. And if the slope of that line is 5, then the derivative would always be 5. And you can do the same thing for a function y equals 7. Y equals 7 is a horizontal line that goes through the y axis at 7, and the slope of a horizontal line is always 0. It doesn't matter where you are looking. The slope is always 0. And so the derivative of 7 would just be 0. Now, just to kind of try to make a point, if you look over here at number 1, this is a cubic graph. And a cubic graph is obviously not linear. It bends around and the slope changes. It looks something like that, depending on the other characteristics of the function. But if you look at this one, my slope is not the same throughout. My slope changes, which is why the derivative has x's in here. So if I wanted to know what the slope was, for example, at x equals 1, then it would be 8 times 1 plus 27 times 1 squared. That would be a slope of 35. That's pretty steep. The slope at 0, when x is 0, would be 8 times 0 plus 27 times 0. So the slope at 0 is 0. And so the slope can change. And matter of fact, it normally does. Very seldom do we use calculus with lines. We use calculus with bendy things that are much more difficult to analyze. So let's look at a few more examples. I think I have 9 total for the power rule. And so number 4 here, we have a bit of an issue because the square root of x is not written as x to a number power. And in order to do the power rule, you really need it written that way. So what I'm going to do is I'm going to change the square root of x to x to the 1/2 power. Now it is written in the format that I need. And 9x to the 4th, that is ready to go. I don't need to change that because that is in prime condition to be differentiated. So I'm going to leave that alone. Please do not, for the love of all that's holy, differentiate the 9x to the 4th and only rewrite square root of x as x to the 1/2. You don't want to have a blend of one thing differentiated and one thing not differentiated. So my function is now rewritten as that, and y prime ends up being 36. 4 times 9 is 36. X, 4 minus 1 is 3. Move on to the x to the 1/2. 1/2 times the no coefficient written, so that's a 1. 1 times 1/2 is 1/2. 1/2 minus 1 is negative 1/2. And technically, you have accomplished the calculus. That is the derivative of x to the 1/2. 1/2 x is negative 1/2. However, in multiple choice situations and in applications later on, it would probably be more beneficial to have this written as a more cleaned up, simplified version. So I'm going to change that x to the negative 1/2, 36x cubed. I'm going to change that to 1 over, and the negative exponent can be moved to the denominator with that too. And then I could even go one step further. Notice I'm not changing 36x cubed. That one has already been differentiated and I don't have to adjust it in any way. I can change square root of x, x to the 1/2 back to the square root of x. And that is a simplified derivative for x to the 1/2 power. Man, that watermark is driving me crazy. And we do the derivatives of root functions, the square root functions, so often, it would be good for you just to remember that if y is the square root of x, then its derivative dy dx is 1 over 2 root x. I'm not a huge fan of memorization calculus. However, sometimes you do things so often that it's a little bit more efficient and helpful to memorize things. And that is one that the derivative of root x being 1 over 2 root x might be worth memorizing because you will see it a lot as you work your way through the year of calculus. Okay, number 5, y equals the 4th root of x to the 7th. Kind of like y equals the square root of x, you want to change the way that is written before you differentiate it. And the 4th root of x to the 7th can be rewritten as x to the 7/4. And now I have x to a number power, which is prime and ready to go for the derivative. It's my derivative for number 5. 7/4 times the coefficient of 1 would be 7/4. And 7/4 minus 1 would be 7/4 minus 4/4, which is 3/4. You're going to get very good at subtracting 1 this year. There's really no need to rewrite that. By the way, this little memorized formula for the square root of x is literally only for the square root of x. Please do not try to apply that to all radicals. It doesn't work for cube roots or the 4th root or the 4th root of x to the 7th. So make sure that you're not overusing that root x differentiates to 1 over 2 root x idea. So looking at number 6, we again have 2 pieces, And the first one is ready to go. 6x to the fifth is fine. 2 divided by x cubed is a problem because the power rule is used for a number times, strictly times x to a number power. So I'm again going to rewrite this as 6x to the fifth. I don't want to change that. The 2 over x cubed we will change by bringing that x back up to the numerator and making that x to the negative 3. Now both of those are ready to differentiate. So my derivatives swap to Leibniz this time after doing Lagrange for a while. So 6 times 5 is 30. X to the 5 minus 1, which would be to the fourth. Negative 3 times 2 is negative 6. X, negative 3 minus 1 is negative 4. If the situation needs it, it might be worth rewriting that second term as 6 over x to the fourth. 6 over x to the fourth. Writing it that way may help you realize some things about that derivative that you don't quite notice, written as 6x to the negative fourth. And I'm kind of foreshadowing things in the future when you are actually using the derivative to answer bigger questions. And then one other thing that I haven't stressed, get in the habit of labeling your equations. As you work your way through the function and the derivative, make sure you label what each line is. So right here on number 4, I did a lot of writing. I had y equals this, and then I have the derivative equals, the derivative equals, the derivative equals. Even if I only have one line, if I change from the function to the derivative, you need to get in the habit of labeling that as the derivative, because the day is coming where you're going to have the first derivative and the second derivative, the derivative of the derivative. And you will have to use those to answer much larger questions. And if you don't have your equations labeled, if you just have floating equations like this, if you don't have y equals or y prime equals, and they're just a bunch of lines, it's going to be very hard for you to find the function that you actually need. If you need the function, if you need the derivative, the second derivative, depending on the level of calculus you're in, you might want to dive into the third derivative. I don't know. But make sure that you are labeling those equations. Make that a habit. You never want to have just floating equations without any label. All right, moving on to 7. We again have an x in the denominator, and I don't like that. I want to fix that. You will learn, if you don't know already, there is such a thing as a quotient rule. We are dividing two things of x, and the quotient rule will work for number 7, but it is much more difficult than turning this into a power rule. So there are 2 ways to do this. One of them is what I call an STD, a single term denominator, an STD. And if you have an STD, a single term denominator, you want to rid yourself of that STD. And so we can do that by grouping each one of these terms in the numerator to putting it over the x cubed, plus x cubed over the x cubed, plus, take that last term, x to the fourth over the x cubed. And you can rewrite this as such. And then once I do this, I have 3 separate terms, and I can reduce those. And I'm going to go ahead and start thinking about the derivative. I know the derivative is on the horizon. And so 2 over x cubed, I'm going to go ahead and bring that x cubed back up to the top, make it 2x to the negative 3. X cubed over x cubed is 1. X to the fourth over x cubed is x. And now I am ready to differentiate each one of those pieces. Negative 3 times 2. X, negative 3 minus 1 is negative 4. The derivative of 1, 1's a constant. The derivative of any constant is 0. And then the derivative of x would be 1. And again, if you want to rewrite that to make it a little bit cleaner, I'll be negative 6 over x to the fourth plus 1. And that's a more simplified version of the derivative for number 7. Okay, moving on to 8, we have an x something times an x something. This is a product. Just like there is a quotient rule, there is also a product rule that you can use to differentiate this. However, even after learning the product rule, I believe it is easier to expand this and turn it into a polynomial. And this one is truly a polynomial in the strict sense of the word. And the derivative of polynomials is pretty convenient. That would become 3x squared minus, let's see, 2 times 3 is 6, x to the first. The derivative of x would be 1, and then the derivative of negative 3 would be 0. So that one ended up being pretty quick. The product rule would be a little bit longer, and you would have more work to clean it up. This is a nice cleaned up polynomial. It's a quadratic for that derivative, and my thing's about to reset. There we go. On the 9, it's going to work out kind of like number 8. We are multiplying two things. And while we could use the product rule, right now I'm pretending we don't know what that is. I'm going to change that x to x to the 1/2, x to the 5th plus 2x. I don't have to change. And then I can distribute the x to the 1/2. Take that x to the 1/2, distribute it through. And when you multiply two x's of different bases, remember that you add their exponents. So 1/2 plus 5 ends up being 11/2. So we have x to the 11/2 plus 2 times x. And here we have 1/2 plus 1, which is 3/2. And now we are primed and ready for the derivative. Bring down the 11/2, x. 11 over 2 minus 1 ends up being 9 over 2. Plus 3 over 2 times 2 is just 3. X to the, and 3 over 2 minus 1 is 1/2. And there's our derivative for number 9. And so there are the examples I have for the power rule. And then I like to go ahead and introduce the derivative of exponential functions at the same time, because the textbook that I use happens to have them in the same section, and it's pretty convenient. So an exponential function, you have to remember, is any function in the form y equals a to the x, and a is any real number. And in calculus, we generally have the base being a positive number. I suppose it's possible to have a negative number for the base. However, with a negative number, you really run into domain issues when x is less than 0, and it gets really wonky. So we'll probably deal only with a's being positive. And I'm just going to give you the rule once my writing board resets. Here we go. So if it's a to the x, then your derivative, dy dx, is a to the x. You copy the function as it is, and then you multiply by the natural log of whatever the base is. A to the x times the natural log of a. If your function is e to the x, which is the most common exponential function that you will see, as a matter of fact, you'll see it probably 95% of the time. You very seldom see bases that are not e, but you will, so be ready for it. Derivative of e to the x, well, that's just a number. E is a constant, and so the derivative follows the exact same rule. It's e to the x times the natural log of e. And you may be wondering, why did I bother a separate one for e to the x? Well, that's because the natural log of e actually cleans up quite sexily. The natural log of e is 1, and so the derivative of e to the x ends up being just e to the x. It is the only non-zero function, at least in AP calculus, that is its own derivative. And so there is your rule for the derivatives of exponentials. And let's put that into practice a couple of very quick times. And so we have the first function, we have a power function, and then an exponential function. So we have a mix of power rule and exponential. And so for number 10, got to wait for my thing to restart. Okay, just had a big issue with my little writing pad thing. Okay, so we will do the power rule for x cubed. Its derivative is 3x squared. Derivative of 3x squared, 2 times 3 is 6, and 2 minus 1 is 1. And then 7 to the x is exponential, so the derivative of 7 to the x will be 7 to the x times the natural log of 7. And that's it for that one. And then for 11, same thing. We have a square root of 10 minus 5 times e to the x. And one thing you have to be careful with is 10 is not a variable. That is a constant. The square root of 10 is a number. So when you differentiate the square root of 10, that will just become 0. And then I'm about to introduce you to a little derivative rule that I'm going to explain in more detail in just a minute. If you have a number times a function, well, I already know the derivative of e to the x is e to the x. If you multiply that by 5, it doesn't change the derivative. So you just keep that 5. You can kind of ignore it. It doesn't disappear, but you keep it. And then the derivative of e to the x is e to the x, and 0 minus 5 e to the x is negative 5 e to the x. And there's your derivative for number 11. And then really quick, the last thing I want to talk about are two simple laws of differentiation. We'll assume that f and g both have derivatives. C is some number. And if you are adding two functions, f and g, or if you are subtracting them and you need to find the derivative, then you just find the derivative separately. We do the derivative of your first function, f, and then we will either add or subtract the derivative of your second function, g. And we have been doing that over and over and over and over again so far in this video. I just haven't explicitly mentioned it, but all of these derivatives where there were multiple terms, you notice I just did one, plus, and then I did the derivative of the next. So while this is technically a good rule of derivatives, you kind of do it intuitively. It's not something that you really need to stress over. It just kind of happens naturally. And then the second one is the one we just used. If you have a constant times a function, it's oftentimes more convenient to completely ignore that constant and then just multiply that constant by the derivative of the function. And that is the end of this lesson. I got a little bit longer than I wanted it to, but oh well.